Okay, let's get started. Welcome back, everyone. How did everything go with your guinea pigs? I mean, family and friends and loved ones and so on. Did interactions go as expected? It's a good question to ask after Thanksgiving in general, right? Okay. Yes?
I learned that my program is pretty terrible.
You learned that your program is pretty terrible. Wonderful. That's what we like to hear. And I'm sure that in report 2, you're going to tell us exactly where it's terrible and so on. Right, everywhere. Okay. Oh, excellent, excellent. So you'll all have plenty of work to do on version 2.0. And you will describe for us what you have planned for version 2.0 in report number 3, which we'll talk about on Wednesday. So report number 2 is due 2 days from now, where you're going to summarize the results of your user testing. Any questions about that? No? Okay, in other news, you all served as guinea pigs for Zemo. It's now live on Steam, and as far as I hear from Jeff, it's doing pretty well. So if you want to go check out Zemo version 2.0, you can go have a look. Okay, so we are getting close to the end of the second last theme of the course, which is looking outward and thinking about computers which are interacting directly with humans here in the real world, right? They're not imprisoned behind glass in a cell phone or a laptop or a desktop. We've looked at 3 different classes of technology, sort of standard technology, embedded devices, which are situated in the sense that they're receiving in real time sensory stimulation from the real world. And finally, the third class are these things called robots, which are basically moving embedded devices. So devices that have a body, they can move around the environment, they can push against the world with their body, and because they're situated, they can observe the sensory repercussions of their actions. Just as a reminder, we introduced robots in Lecture 20. We talked about situated and embodied cognition in Lecture 21. In Lecture 22, we added some new things to our robots' environment, and these things are called humans. And we talked about some of the particular kinds of interactions that are important when robots are interacting with people. And today we're going to work our way through Lecture 23, which is robot-robot interaction. So now, from the robot's point of view, there are other things in its environment which are robots, which also sense and act on their environment. We're going to think about those particular kinds of interactions between robots, and we're going to think as HCI designers how we can design those interactions so that the robots as a swarm can do something collectively that's beyond the ability of any one robot. Okay, I'm pretty sure we're going to finish Lecture 23 today, and we will start in on Lecture 24, which is the Twitch Plays Robotics project. This is a project done by one of my graduate students, Joey Netzberger. Joey took this class 2 years ago. When she graduated, she joined my lab as a PhD student. She took the HCI class and the robotics class and sort of put some of the ideas together to create the Twitch Plays Robotics project. So I'll tell you a little bit about Joey's project next time. If we finish early, we might get into Lecture 24 today. I just put up the slides now. I apologize. There's a lot of embedded videos in Lecture 24. I don't think they'll play if you download this one. I'll check when I get back to my office. I'll update the slides for Lecture 24 so that when you download it, you can play all the embedded videos. Okay, let's see. Anything else to report? I don't think so. So let's go back to Lecture 23, robot-robot interaction. So you remember we've been drawing this cartoon where we have R, the robot, which is acting or generating behavior. And if we have multiple robots, some of the actions of some robots become the input or the sensation of another robot, and in turn, the actions of that one become input to the other one, right? So now we have RRI, robot-robot interaction. We ended class last Friday with this video of the zooids, this little robot swarm moving around on a desktop, and they were collectively moving a smartphone. What was the main message that we took away from the zooids video? Bradenberg, right? So Valentino Bradenberg taught us that if we think carefully about the robot's environment and in this case the environment is other robots, we can often get away with writing just a few lines of code for our robots. We can create relatively simple robots that when we put them together exhibit the desired behavior because they're exploiting this interaction. And we're going to see lots of examples of that today. Okay, so let's go back in time again, and we're going to visit a particular pair of robots known as Machina Speculatrix. How is everybody's Latin? What do you think this means?
Machines.
Machines, yes, machina is machines.
Machines that speculate.
Machines that speculate, exactly. And like Bratenberg, there's two levels to this. There is the speculating that the robots do, and I'll play you the video of the Machina Speculatrix in a moment, but there's also the speculation that we do. When you watch these robots interacting with their environment, the idea when these were made was that it might change your thinking about thinking. So the robots are speculating, but Gray Walter built these robots in order to change our speculation about intelligence. Okay. No, this is not a
In a
spoof
simple
video.
villa on the outskirts of Bristol lives Dr. Gray Walter, a neurologist, who makes robots as a hobby. They are small, and he doesn't dress them up to look like men. He calls them tortoises, and so cunningly have their insides been designed that they respond to the stimuli of light and touch in a completely lifelike manner. This model is named Elsie, and she sees out of a photoelectric cell which rotates above her body. When light strikes the cell, driving and steering mechanism sends her hurrying towards it. But if she brushes against any object in her path, contacts are operated that turn the steering away, and so automatically she takes avoiding action. Mrs. Walter's pet is Elmer, Elsie's brother, in the darker vest. He works in exactly the same way. Dr. Walter says that his electronic toys work exactly as though they have a simple two-cell nervous system, and that with more cells they will be able to do many more tricks. Already Elsie has one up on Elmer. When her batteries begin to fail, she automatically runs home to her kennel for charging up, and in consequence can live a much gayer life.
So if lithium-ion batteries existed back then, we
What?
would have had Roombas a long time ago.
That's right. I was going to ask you, does this robot look familiar? Okay, there were a lot of cultural references in there. When was this video made? 60s? Go, keep going.
70s.
Late 40s. This was, I believe, 1948, 1949. So, if anyone asks you what the first modern robot was, this is it. Elmer and Elsie, the two Machina Speculatra. Okay, so not very sophisticated, but amazing given the technologies that was available at the late 1940s. This is a replica that was built in the 90s by one of my colleagues. So the next time you're at the Smithsonian in Washington, D.C., you should be able to go and see this is a replica of Elmer. Elmer and Elsie were slightly different. The nice thing about the transparent dome is you can see all of the analog electronics inside. So obviously this was long before digital electronics. Pretty impressive. It was a little hard to see in the video, but there was actually some phototaxis going on. Actually, it's the opposite of phototaxis, photophobia. So Elsie at the end goes inside her hutch where it's a little bit darker. This was 20, 30 years before Bradenberg's vehicles. How do you think this was accomplished?
Is it just looking for the darkest spot in the room?
It has this circling sensor on top, so just one sensor.
You did put a giant white square over the charging station.
Yeah, that might have helped to increase the light gradient. So Bradenberg showed us that you can get phototaxis with two light sensors, right? Turn towards the brighter of the two sensors, or if you want photophobia, turn away from the brighter of the two sensors. You can also do phototaxis with just one turning sensor. How?
Contrasting the light levels at each interval rotation.
Exactly. Remember we did the thought experiment a few weeks back with the Lego robot that was turning on the spot, right? You sort of, as it's turning, there's a little bit of memory in here, which was possible with analog electronics even back then. And it's sort of comparing light levels, right? So as this wheel is turning, it can sort of figure out whether things are getting lighter or darker. If it wants to go towards darkness, and things are getting darker, then keep going, and if not, turn. So you can still get a lot of the Bradenberg type vehicles even way back in the late 1940s. Okay, so the reason I wanted to bring up Gray Walter's tortoises is, again, he anticipated Bradenberg by about 20 or 30 years. He wrote an article, Popular Science article, 1950, called An Imitation of Life, and again, this looks pretty familiar. So back then it was hard to take a photograph and put it in a magazine. Much better to do an actual line drawing of what happened. So here's one robot, one light, which gives you phototaxis. Here's one robot and two lights, which gives you exploration. This should remind you of a particular Valentino Bradenberg vehicle that we saw. Which of Bradenberg's vehicles was curious? The Explorer, right? So Bradenberg sort of stole this idea from Gray Walter 20, 30 years earlier. Owen Holland down here was the one that made the replica, and he wrote an interesting article about this. It's got a lot to do with the history of robotics. If you're interested in that, it's an interesting read. In this 1950 article was the following drawing, in which now you have the first, not just the first robot, but the first robot swarm, Elmer and Elsie, performing the mating dance. And you can see a little bit of that in the video. What else is different here? What else has changed in this image compared to the first two?
They each have a light attached to them.
They have a light attached to them, right? So what happens when one of them starts to perform this spiral? What does the other robot sense? Senses a changing light level because the light bulb that it can see on the other robot is moving relative to itself, which causes it to move, which causes its light to affect the other robot, and it produces this complex pattern in which they approach one another and then move away and approach again and so forth.
Is that one the coward?
This one is that's a good question. You can actually go back and have a look through the Bradenberg vehicles. I think it's not the coward, I think it's actually the Explorer, because if they're cowards, they would just drive away from each other indefinitely, right? Okay, so the first example way back in 1950, again, that if you think carefully about the interaction between multiple robots here, again, at the beginning of when computers were starting, you start to get this interesting and rich behavior by thinking more about the interaction between the robots rather than what an individual robot is doing. Okay. Let's move forward in time a little bit. So obviously, if we want to build robot swarms, there are a lot of examples of swarms in nature. Here's a great example of a particular species of birds doing what certain species of birds do best, flocking. Any biologists here? Any ornithologists? These are starlings in the UK, which can produce spectacular flocks up to tens of thousands of birds. Which bird is in charge here? Which bird is saying, now head this way, now head that way? So how do they pull this off? If there's no one leader, how does this work? Exactly. So the heuristic you just pointed out, change your direction and heading based on the direction heading of your closest neighbors, that's sufficient to produce all sorts of collective behavior. So back in the 1980s, a computer graphics specialist, Craig Reynolds, took that idea and started to build it into what became known as boids, so biological robots or something like that, where basically each boid in the swarm is running 3 different heuristics. And here's a picture of each of them. And this has been used ever since in Hollywood films. So let's watch The Lion King. This was the first attempt to incorporate boids into a Hollywood movie. You're going to see some swarming in a moment. Pay attention to how the wildebeests that you'll see in a moment perform their collective behavior. Okay, so we've got this simple heuristic in there where the wildebeests are changing their direction and heading slightly based on what the neighboring wildebeests are doing, but they weren't just responding to neighboring wildebeests, they were also responding to the terrain itself, right? So it's a little difficult to see in this case, but in this box canyon, there's a little spur of rock and they flow around the rock. Why does a group of animals, or boids in this case, collectively split and flow around the rock and meet on the far side? How do these kinds of heuristics give that behavior?
So like a minimum distance they need to keep between each other and also obviously avoid objects.
A minimum distance and a maximum distance, right? So if there's a lot of stuff on your right, move to the left a little bit. If there's a lot of stuff to your left, move a little bit to the right. Doesn't really matter whether that stuff is a wildebeest or a hyena or a spur of rock or what have you, right? Okay, so the specific 3 heuristics that were in the original Boyd's algorithms were separation, alignment, and cohesion. So each boid is running an infinite loop, and every pass through this infinite loop, it's computing how its direction and heading is going to change according to these 3 heuristics. So separation, you look at your nearest neighbors. So in this cartoon here, our boid in the center here has a sphere of sensation, so it can only see, in this case, these 3 neighbors. It counts, or it looks to see where the neighbors are relative to itself, and then moves slightly away or changes its heading slightly away from that. So in this case, the bulk of its neighbors is on its left, so it's moving a little bit to its right. If it had 5 neighbors, 4 of them on its right and just 1 of them on its left, there would be more mass on its right, and it would turn a little bit to the left. So in this infinite loop, the output from the separation subroutine is a delta, saying change your heading a little bit to the left or a little bit to the right. The second subroutine, called alignment, is also outputting a delta or change in the heading, The alignment subroutine is looking at not the relative position of the neighbors, but their heading. So we're assuming here that the Boids can not only see the neighbors and where they are relative to itself, but also the heading of those neighbors. In this case, the Boid computes the average heading of all of the neighbors, which is indicated by the little blue tick originating out of the center Boid. So that's the mean heading of all of its neighbors. The green tick is its current heading. And the output of the alignment subroutine is a new heading, a delta heading that's a little bit closer to the blue tick, right? So turn in such a way that you're starting to line up your heading with the rest of the flock or the herd or the school. Okay, finally, cohesion is like the antithesis of separation. Again, look at the relative positions of your neighbors. Take the positions of your neighbors and take the mean of those positions, which is the blue dot here. So what is the center of mass of your neighbors? And turn your heading so that you're heading a little bit towards that center of mass, right? So if you're on the edge of the flock or the school and you're starting to drift away, cohesion will bring you back towards the center of the flock. Okay, so we have this infinite loop running. At every iteration through the infinite loop, the Boid calculates a delta in heading output by each of these three subroutines, which give you three changes in heading. So maybe separation says turn a little bit to the left, alignment says turn 30 degrees to the right, and cohesion says turn to the right 10 degrees. You take the average of those three deltas, which collapses back down to one delta heading. So one change in heading. What do you think the Boid does when it exits out that iteration of the infinite loop? It changes its heading according to that delta, right? So it changes its heading a little bit, goes back into the infinite loop, does it all over again, and every single Boid in the swarm is doing exactly the same thing. And that's enough to give you the behavior you saw in the Lion King clip there. Yes?
Is this the sort of thing that autonomous cars use?
This is, yes. So in the current state of the art in autonomous cars, at the top is something like this. The hard part is detecting cars and shadows and pedestrians and changing lights and so on. Once an autonomous car is aware of exactly what's around it, then yes, an autonomous car is not much more.
Like a flock of, autonomous cars, then it would be easy enough to program.
Absolutely, right? So if you have a bunch of cars going down the highway, align your heading so that it's pretty much aligned with the other cars and the lane markers and so on, right? The hard part, again, is detecting what these things are that's around you. Okay. I think I have a video here of Reynolds' original Boids. This was back in, I think, the mid-'80s. As you can tell from the quality of the video. Okay, state of the art back in the mid to late 80s. What happens if we took Reynolds' swarm and we deleted the third subroutine? So now all the Boids were only changing their heading based on separation and alignment. We take a whole bunch of Boids, download the changed code, turn the code on. What does the swarm do?
This one will eventually start pushing itself wider and wider and wider.
Absolutely. It'll start to disperse. What else? Not just disperse. Is every Boid going in different directions? Let's say we take the initial swarm, we put them at random positions, and we give every Boid an initial random heading and turn them on. Yes, they will slowly start to disperse because they're lacking cohesion, which will pull them back together. But how will they disperse?
traveling alongside each other?
That's right. So they're still running alignment, right? So as they're moving away from each other, they're also going to start to try and align with their neighbors somewhat, right? So they'll head off in different directions, but sort of in similar directions. Okay, so you can build up an intuition of how these subroutines influence the collective behavior by thinking about what would happen if you reran the swarm missing one or two of these simple routines. Again, like Bratenberg, you get relatively sophisticated behavior like a swarm that flows around objects and meets on the far side without having to write recognize obstacle, decide which side of the obstacle to go around, and once I go around it, look for my neighbors and realign with them, right? It falls out of the fact that these voids are interacting with each other and with the obstacles in their environment. Okay, here's a somewhat more recent example. When I was a grad student in Switzerland, there was another grad student working on the Swiss robots at this time. They weren't just Swiss robots because they were being built in Switzerland, but it's because they like to keep everything neat and tidy and clean. Here's a cartoon of this robot here. There's a bunch of them. They were placed inside a large arena with these styrofoam cubes. Each robot, like Bratenberg vehicles, had 2 motors, and in this case 2 distance sensors, so they could see if there was a wall or another Swiss robot or a cube nearby. The control algorithm also looks quite a bit like a Bratenberg vehicle. If there's stimulation on the left, so if there's something on my left, turn to the right. If there's stimulation on the right, turn left. If no stimulation, go forward. So if you take this hardware in this environment and download this software into the Swiss robots, over time, they gradually clean up this arena by clumping all the styrofoam cubes together. Why? There's one detail here that I haven't talked about which makes this possible. What is it? If you remember your Bratenberg vehicles, this control algorithm here would make you think that the Swiss robots never go anywhere near a styrofoam cube. How do they ever get close enough, let alone push a cube? Right? This is the coward. They're afraid of styrofoam cubes.
Is it because the sensor is a touch sensor, so like it has to hit it to be able to?
It would be if it was a touch sensor. It's not a touch sensor. It's a distance sensor. So it's emitting a reflected beam of light, and it's looking to see how long it takes for that beam of light to come back, and it gives it a distance reading. How far away is something? You would think that if you put a bunch of these Swiss robots in this arena, they would just move away from each other and the cubes and the walls of the arena, and they would never clean anything. The clue is hidden in this cartoon at the bottom here.
So if it has something directly in front of it, it doesn't say anything about stimulation to what's directly in front of it. So it's going to keep pushing whatever's in front of it or moving towards something that's directly in front of it until it gets stimulation on the left or right. Once that happens, it will move towards that and start pushing that one.
Absolutely. So we talked about the sensors and the motors and the software and the environment. The one detail I left out was the body itself. So in the cartoon here, you can see that the distance sensors look diagonally, front left and front right, and deliberately the Swiss robots have this snub nose. So if they happen in their movements to approach an object head on, they do not see that object. So if no stimulation, go forward. And if they go forward, they will just crash into it and keep pushing it as they move forward. What causes that pushing behavior to stop? They run into another one. So in the cartoon here, you can see there happens to be another styrofoam cube front left. At some point, as the Swiss robot is pushing this cube, it sees the one front left, and because it's the coward, it turns to the right. And what happens to the cube it was pushing?
It's left and right
It's left there, right? So it's left next to the other one. So we get the collective behavior that we're after, which is cleaning up this arena, by thinking carefully about interaction, right? So we're thinking again about sensory interaction, but also we're thinking carefully about physical interaction, right? We want this robot to push these blocks and to stop pushing them when it gets close to a protopile, right? So as we move forward and start to develop the Internet of Things, and those things are physically interacting with the environment, it's not enough just to think about the code and the sensors and the motors. We have to think about the actual shape of the device itself. We've already seen that a few times in our HCI examples, right? We have to think about the ergonomics or the shape, how this thing exists in the physical world. And by thinking about that and sculpting all of these things together, we can get sophisticated behavior like cleaning or clumping with nothing more complicated than a Bratenberg vehicle. Okay, let's keep moving forward. We obviously would like to develop a robot swarm because there are certain things that are difficult for any one robot to do on its own. But what size of a swarm are we talking about? So if we're going to build hardware robots, it's tricky, right? Maybe we can do a few tens or a few hundreds or maybe a few thousands. How do we scale up this idea to very large numbers of robots? So let's have a look at, if I can find it here, James McClurkin's swarm. I cannot seem to find it here. Hold on a second. Ah, good. So here's an example of a swarm performing division of labor. Okay, so our robots here each have a red, blue, and green light that they can switch on, and they can advertise which team they'd like to belong to. And then they need to go and find their team. In this particular implementation, each group elected a leader, and that leader admitted its position, and red leader would wave all the other reds towards it, and the blue leader would wave all the other blues towards it, and so on. And the result is what you see here. Worked well for this group of 20, 25 robots. Not going to scale very well. Why not? What makes this particular approach not very scalable?
The more robots you have, the slower it's going to take for them to get together.
The more robots you have, the slower it's going to take for them to get together. Yes, that's true. But what about this particular? What is it about this particular solution that's going to cause that slowdown?
The distance they have to travel to get around the robots.
Yes.
Is it because the leader of the group is going to be so far inside the group itself?
So for sure, the leader is going to probably get surrounded eventually.
They don't account for the other, they just try to beeline for the leader and they're going to bump into each other.
Absolutely. So as you scale things up, we're going to get a lot more congestion. So there's a lot of other scalability issues we need to deal with. So maybe we layer some more Bratenberg vehicles on top to avoid robots of the other color. Will this work? What if we went up to 10 or 100 or 1,000 or 1,000,000 robots? And red leader is attracting its robots and blue leader is attracting its robots. Again, think about physical context here. You can see the size of these robots. If we did this with 1,000,000, we'd have to be doing it in a football stadium. What's the problem? Aside from slowdowns and traffic jams and so on.
Could it be detection problems?
Detection problems, exactly, right? So maybe red leader is at one end of the football stadium and a particularly unlucky red robot is at the other end of the stadium. Does a robot this size have enough transmission power to send out its position, right? like human organizations, they become increasingly difficult to organize when you grow to larger and larger groups, and more responsibility falls on the shoulders of just one individual. How could we take the same hardware and change it into a more distributed solution so we didn't have to rely on one leader?
Well, you could have a leader and then like sub-leaders that can spread out and detect robots that are farther away. So once they get all the robots that are farther away, then they can go back to the main leader.
Absolutely, right? So as good computer scientists, we could take this problem and recast it as a recursive solution, right? Sub-leaders and sub-sub-leaders and so on, which is what some human organizations do.
If they can't find the main leader, path towards the nearest other red.
Absolutely, right? So find someone that belongs to your team. What if you're really unlucky and you can't even find someone that belongs to your team?
Did you say they could change teams?
I don't know if they could change teams, can they? I don't think so. Let's assume they can't.
You can move away from the other teams.
Move away from the other teams, or maybe blue team says red team is that way, right? You could come up with a hierarchical or recursive solution where you have leaders and sub-leaders and sub-sub-leaders. If you think carefully about this, you could probably come up with a completely distributed solution like Craig Reynolds Boyd's or like Valentino Bradenberg's vehicles, where it's completely distributed, right? If I'm red, I move towards blue light, or I move away from blue and green light and towards red light, period. That might be sufficient. You might have to tweak it a little bit to avoid, traffic jams, but you might be able to get away with a completely distributed solution.
I mean, this is probably more complicated than we need, but you could also increase like what the number of dimensions they can move through. That would probably reduce congestion.
Yes, we could put a drone on top and they could move in 3 dimensions, perhaps. Okay, so the reason I wanted to show you these examples again is when we think about trying to create software for a distributed network of physical machines that can move, we need to think carefully about how centralized a solution and how distributed a solution we want to come up with. And we want to try and err on the side of a distributed solution to make things robust and scalable. Okay, so we just talked about the problem here. So a lot of work in distributed robotics or collective robotics is this idea of decentralized control. A particular class of robots that takes this to its extreme are modular robots. So a modular robot is a robot swarm in which elements of the swarm can physically attach and detach from one another. Here's one of the very first modular robots that was ever built. This is Polybot, developed back in the 90s at the Xerox PARC Research Institute. So in a modular robot, the modules can connect and disconnect with each other, and they can also only talk, or usually only talk, to their immediate neighbors, those neighbors that they're connected to. Okay. Here's a more recent example of this idea, this modular robot. Let me show you, actually let's describe it first and then we'll watch the video. So in this case, every element in the swarm, which is a module in this meta robot, is running exactly the same code, so everyone gets the same instance of the code, and each robot in this swarm is going to perform some action, and which action it performs depends on how many neighbors are attached to it. So if a particular unit has 2 neighbors attached to it, this unit is going to send commands to its motors to move in a particular way. If the same unit detects 3 neighbors, it's going to move in a different way. And so all units are running exactly the same code. So in this case, we have all of the units in the Conroe robot attached in a snake formation. Which units are going to move in the same way, and which units are going to move in a different way when I start the video? We've got 1, 2, 3, 4, 5, 6, 7 units here. which ones are going to move in the same way and which ones are going to move differently. So an element in the middle here has how many neighbors?
2.
2. This unit here has how many neighbors?
1.
This unit has 1, right? So the two end pieces, whatever they're going to do, they're going to move differently than the interior pieces, all of which have 2 neighbors. Okay, so they're turning the robot on. So the front unit is going to start moving first, and it's going to propagate. Oh, I'm sorry. It propagates the signal to the back, and along we go. It's a little difficult to see in this video that the back segment and now the front segment are doing the same thing, and the middle ones are doing the same thing. The nice thing about modular robots is they don't have a fixed body shape. What's happened to this unit? It now has 3 neighbors. This unit now has 4 neighbors. Which means this unit is now doing something different from all the other units, because there are no other units that have 4 neighbors. So again, all the exact same code, but in essence, 2 different robots performing 2 different gaits or ways of moving. So the interaction here, again, that little cartoon of I act and I sense the repercussions of my action is pretty limited, right? What they sense is just an integer reporting how many neighbors, if any, you have. And then the output is some case statement, which is if I have 1 neighbor, output this pattern. If I have 1 neighbor, output this pattern, 2 neighbors, this other pattern, and so on. Okay. That's video 1 of 2. I'm going to play the second one in a moment, and you can imagine what you're going to see in the second video. I'm going to show you the same robot, similar robot, slightly more sophisticated coding. No guesses? Okay. Not the most sophisticated robot you've ever seen, I guess. Which is scarier, Jibo or Conroe? Jibo's still scarier? Okay, all right. Usually the vote's a little bit split. Okay, so again, for a lot of practical tasks, we might want to have a fully disconnected swarm where every robot is off doing its own thing, but there might be other tasks we would like a robot swarm to tackle where they might need to physically connect and in essence grow larger. Can you think of some task environments in which that might be true? Aside from the eye candy value of these videos, why might you want to create robots that can reconfigure on the fly?
If they're traveling across certain terrain, if they reconfigure, they can do it easier. Or if they're like stuck somewhere, they can like reconfigure to get themselves unstuck.
Absolutely. Yes?
Something can break, so we might need to reconfigure to account for that.
Absolutely. So there are other modular robots that physically spit out a dysfunctional part, right? So if they're moving through an irregular terrain or if there are obstacles that are taller than the height of an individual element, by definition, they're going to have to connect in order to get over that obstacle. Okay. This one's kind of just for fun. This is, again, a modular robot, which arguably is the first self-reproducing robot. This robot, assuming that you keep giving it new robots or new pieces, will connect to them and is running, again, a program that moves depending on its neighbors and will create a copy of itself. If you take, oh, it's still building its child. So again, we have to put the blocks in exactly the right place. You'll see that the child is now participating in its own production. Take away the parent, and the child will produce the grandchild, and so on and so forth indefinitely. Luckily, this is not going to lead to runaway self-reproduction of robots because they run out of gas as long as we don't give them any more food, so to speak. Okay, we've got 5 minutes left, so I'd like you to turn to your neighbor and again do a little bit of brainstorming on how we would deal with this particular task environment, which is a large-scale disaster site. This is a very particular environment. It's three-dimensional. The size of the apertures are fractal, meaning that they're self-similar, so there are a lot of few small holes, lots of small holes. They tend to have the same kind of topology as you get smaller and smaller. How would you design and then deploy a modular robot that could collectively explore this environment looking for human survivors? So you can keep this at a pretty high level like you've seen in this lecture. Start to jot down some sort of basic heuristics